The depth of the water in a river of width 20 meters was measured at intervals of 4 meters, start from one bank and at the other. The results are recorded in the following table. Use the trapezoidal rule to estimate the area of the cross section of the water at this point, so we just gotta get the area of it. Okay, so all we gotta do here is, okay, if you imagine that this is the level of the river. Okay, this is the water level of the river, and then at the start the depth is 0.6, so it's actually, there's different depths as it goes along, okay? So it's going to be, that's going to be 0.6, this one here is going to be 0.8, slightly longer, 8 is going to be 1.4, which is longer again, this one, 12, is going to be 2.1, so that's going to be even deeper, 16 is going to be 1.9, and then finally 20 is going to be 0.7, and 0.7 is just supposed to start. Now, if I was to link all these, okay, now the bottom of the river is obviously unequal, okay, so what they're doing is they're just measuring, this is the river. Now the river is actually going back into the page, so if I was to try and draw this in 3D, the river would be coming at you like this. Okay, that's basically what's happening there. This is a river full of water coming your way. Okay, so what we gotta do is we gotta get the area of this full face. Okay, so look, it's 0.6 the start, 0.7 is the end, and you know the formula. It's width over 2. So what's the width of each one? The width is 4. Okay, so to go across in 4. So the area is trapezoidal rule. So this is here. Area equals width over 2, which is 4 over 2. Brackets. What's the first? Is 0.6, the last is 0.7, plus 2 times the remaining, which is going to be 0.8, plus 1.4, plus 2.1, plus 1.9, close bracket. What does any of you get for that when you put it in? 7.4. Is that correct? Anybody else get 27.4? Yeah. Is that what's in the back of the book? Yeah. Okay. Area of this is 27.4 what? Meters squared. Okay. At this point of the river, it was calculated that the water was flowing at a speed of ½ meter per second. Find the volume of water passing this point each minute. A in cubic meters and B in liters. Okay. So what we did earlier in the course is this. What we said was, if you have a cross face of a certain area, so imagine this is your, sorry, that's a badly drawn river. Imagine this is your river depth. It goes back up. Now what we said is you can always multiply your area by your length, and that's how we're going to get volume. Volume equals area by length. So in this case, the area is what, guys? 27.4. And the length, now we have to figure out the length. It's ½ meter per second. So what we're going to do is we're going to multiply this by ½ meter. Okay? And what's that? So 27.4 multiplied by 0.5. And what we get there is 13.7. That means there's 13.7 is a meter squared or meters cubed for volume? Meters cubed. There's 13.7 meters cubed of water going through the river every second. The reason why it's per second is I only used ½ meter. I want it per minute. So what do we need to do there? Multiply by 60, okay? So 13.7 times 60. 822. So there's 822 meters cubed per minute. Now, the problem here is it wants it in liters. Okay, that's the answer to part A. Part A wants it in meters cubed. We need to figure out a way of converting meters cubed into liters. Now, anybody who remembers this is what I do, okay? I'm going to draw a cube, haven't I? I'm going to draw 2 cubes, and I'm going to explain why in a second. There's one, and here's the second one. Okay? So that one should be. Yeah, it will be the same size. Like they're meant to be the same size, as good as I can get them. Okay.
Yeah, sorry, I mean about that. I mean, as in like down to how much converting plus 1,000 liters.
I have to convert it into liters for the second question. Actually, tricky enough. So here we go. Okay. What's going to happen is, the way I always do my conversions is like this. Okay. I have meters cubed. I'm going to draw down a cube that has 1 meter cubed. Okay, 1, 1, 1 meter, meter, meter. Okay. Then what I do is I look at a similar shaped cube, except this time I'm measuring it in centimeters. They're actually both exactly the same size, but this time it's 100 by 100 by 100. So basically, 1 meter cubed equals 100 multiplied by 100 multiplied by 100 centimeters cubed. So what's 100 by 100 by 100? I think it's a million. Yeah. It's 100 to the power of 3. It's a million, okay? So 1 meter cubed equals a million centimeters cubed. Then all we got to do is convert 822. So 822 meters cubed is going to be 822 million centimeters cubed. Now, once again, I'm still not in liters, but now I know the conversion. What's 1 liter, Kane, in centimeters? 1,000. So what do you think you need to do with that answer there? Divide by 1,000. 3 zeros, right? So get rid of 3 zeros. 1, 2, 3. So the answer is going to be 822,000 liters. Anybody get that?
Yeah, no.
This one here, right, is a function, and what you'd ideally like to find out is what are the heights going up here, here, here. You want that one as well, and you want this one here, and you want the starting one. Now, the problem is sometimes some of them you can read off the graph, can't you? So the likes of the first one, likes of this one, I can say it's 3. The likes of this one here, which is for 4, I can say that's 18, and the likes of that one I can say is 27. But the problem is there's some of them that don't fall exactly on a line, therefore I can't really read them. So what you're going to do is you're going to go to the calculator, you're going to go to your table function, which is number 3, and what you're going to do is you're going to put in this formula here, x squared plus 2. Okay, you're going to start at 0. And you're going to end at 5. Now, step is 1. The reason why I know the step is 1 came? 0 to 1, 1 to 2, 2 to 3. Okay. 0, 2. The first one is 2. This one here is 6. Number 3 is worth 11. And then it's 18 and 27, which you already know. 11, 18 and 27. Connor? Sorry? Okay. Next one is area equals width over 2. First plus last plus 2 times remaining. Okay? Now, what's going to happen is we're going to do the width, and the width is going to be 1. 1 is the width. Okay? So Keane, this is what you were asking me a second ago. It's going to be a half. The first is 2. The last is 27. 2 times the remaining is going to be 2 bracket 3 plus 6 plus 11 plus 18 close bracket. Now, all we got to do here, if I ignore the half at the start, Kim, so this time I'm going to ignore the half, okay? I could put it right into the calculator if I wanted, but there's sometimes it's best just to do it this way. So look, we're going to do 2 plus 27 plus 2 times, so it's 2 multiplied by everything in here. 3 plus 6 plus 11 plus 18, okay? Now to stop here, that's 105. So it's going to be a half of 105. And that will get me 52.5 meters squared. Is that right? The actual area between the curve and the area x-axis is 51 2/3. Find the percentage error in the estimate correct to 1 decimal place. Okay, so once percentage error, I gave you the formula the last day before I left. Can anybody remember the formula for percentage error? Error over actual value multiplied by 100 over 1. Okay, so to get the error is going to be 52.5 minus 51 2/3. That's what the actual error is. So we'll just put that into the calculator and see what we get for the error. Please remember the mixed fraction button. You can see it's in yellow, so we just press shift this button here, and then you can get your 51 2/3. Okay. For anybody who wants to know where I got that again, it's see the yellow button above the normal fraction button. To make anything, if you want anything in yellow, press shift. If you want anything that's written in red, press alpha. Okay. And what we get there is, it looks like 0.833, okay? So error is 0.8333, okay? More decimals equals more accuracy. Okay, so just write down a couple of trees to make it really accurate. Next thing, percentage error equals error over actual value. Now this is the problem that most people make, is they get confused which value they're meant to use on the bottom. Which value am I actually meant to use on the bottom? Is it 52.5 or is it 51 2/3? It's 51 2/3 because the question says this is the real volume of the lake. It actually says the area is this. Okay? It's not a lake. Alright? And then it's going to be over 51 2/3 multiplied by 100 over 1. So whatever answer I got here, what we can do is we can say answer divided by shift 51 2/3. Okay, paying attention there, guys? Andrew? 51 2/3. Shh. Okay, then you're going to multiply by 100 over 1. Now what we get here is 50 over 31. Okay, 1.6%. Okay, so that's our error is 1.6%. Okay. Next thing. So that's our error, okay? Back to the question. Comment on how effective you think the trapezoidal rule is in this case. Now, I'm going to explain to you why there's an error, okay? So for those of you who don't know what the trapezoidal rule actually means, it means this, and I'm going to make this a lot bigger now, okay? And I'm just going to redo it. Now I'm going to actually show you what actually the trapezoidal rule is actually doing to calculate the area, okay? So if you imagine, okay, every straight line, and you need to know this, every straight line I draw up, okay, there's an object called a trapezium, okay, and you guys know that a trapezium is basically, it has two parallel lines, but the tops can be slanted from each other, okay? So what this is actually doing is it's calculating this area here. See the way I'm going straight across with the top line. Now what you can see is it's missing, it's either adding on or it's basically adding on a small amount of the, well, we got a bigger answer, so it's actually adding on area, okay? Because if you zoom in, you can see that the dotted line is actually above the blue line on more than one occasion. This means it's adding in area. That's why it's an estimate. It's a pretty good estimate, but it's not the best estimate. So for instance, if I had a curve like this, okay, and I had my height between these 2 points here, what the trapezoidal rule would do is this. It would add on, it goes straight across from peak to peak. So what it's actually doing is it's actually adding on a small bit of area each time. That's why the trapezoidal rule isn't 100% accurate, okay? So just remember that in a test situation that it's actually going straight across from point to point, and it's not actually following the curve. That's why you get a different answer. Is that alright? Did you know that before?
Yeah, no.
Okay. Now, comment how effective you think the trapezoidal rule is in this case. With an error of 1.6%, I would say that the trapezoidal rule is quite effective. How would you reduce your area? Error? Can anybody tell me? What would be a good way of using the trapezoidal rule again, but this time you get less error? Okay, the more height you use, the less error you get. So if we did this again, and this time we made the gap every half, and we used more points and more heights, what you'd actually find is that, like, if I do a zoom in here, imagine I put a point in between them, yeah? And I'm going to use a red dotted line to show you what happens when we double the amount of heights we're using, okay? Look at this. From here to here, and here to here. Which one has more, which one goes outside the curve more? The red line or the black line? The black dotted line or the red dotted line? The black dotted line adds on extra area, while if you cut it in half, the red line adds on less area. This is the reason why more heights are more accurate than less heights. You got that, lads? Yeah. Okay. Long story short, in the exam, if you want a 10-second learn off, the more height you have, the more accurate your answer. The less height you have, the less accurate your answer. Okay? Now finally, 18. Okay, Kim? 18. A geography class is required to estimate the area of Carlingford Loch from a map with a scale of 1 is to 70,000. What does that mean? Can anybody tell me? 1.70,000. Centimetre. Every centimetre on this graph is going to be 70,000 centimetres in real life. Okay? An axis line A, B, C, D, E, F is drawn and divided into 5 equal segments, 3 centimetres each. 3, 3, 3, 3, 3. Can somebody do me a favour? Okay, there's going to be 2 lengths we need to measure. Okay, we have to measure D and E. So if somebody can get out a ruler there and just measure what it is going through D, straight through D, across from side to side, and straight through E from side to side, and just call out what it is. Okay, guys, this is 4.5, and this here is 3. Okay, 3 and 4.5. Okay, so what we do is just replace D with 3, E with 4.5, and we get going. Use the trapezoidal rule to estimate the area of Carlingford on the map in centimetres. Centimetres squared, okay? So here's how we're going to do this. Are you ready, lads? Centimetres squared, okay? Width over 2. So what's the width?
3.
3 over 2. Bracket. First?
0.
First is 0. Last? 2.5 plus 2 times remaining. It's going to be 3.5 plus 3.5. Don't have enough space, just give me a second. 2.5 plus 3.5 plus 3 plus 4.5. Will somebody try that on the calculator for me, please? And see what you get. Hey guys, come on, everybody try it out so we know we all agree. 3 over 2. 2.5 plus 2 times 3.5 plus 3.5 plus 3 plus 4.5. Okay, let's see what happens here. 189 over 4?
No. Yeah. No.
Okay, 47.25. Okay, centimetres squared. Now here's the problem, right? And this might come useful to you in your geography as well. Okay, the area, it wants it in kilometres squared. Now here's the problem. Okay, if 1 centimetre equals 70,000 centimetres in real life. So this is map and this is real. Okay? What is 1 centimeter multiplied by 1 centimeter? 1 centimeter by 1 centimeter is 1 centimeter squared. What do I have to do to the right hand side? 70,000 multiplied by 70,000. Okay? What is 70,000 squared, anybody? Shh, lads. 70,000 squared. It's a very big number. How many zeros do we have? 1, 2, 3, 4 by 6. I have 8 zeros, don't I?
Yeah, 4 billion.
Okay, that's grand. 49 and 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. That's okay. Now, the next thing is it wants this is currently centimeters squared. Okay. Next thing I have to do is I have to convert meters squared into centimeters squared. This is 1 meter squared here. And 1 meter squared is the same thing as 100 by 100. Yeah? And what's 100 by 100? 10,000. Okay. Part 1. If 1 meter squared equals 10,000 centimeters cubed. Now this is very important. This is stuff that we have I lost anybody yet? In all honesty, have I lost anybody? Okay guys, what happened next is we're 47.25, okay? So look, we got to multiply this number by 47.25 to actually convert it to, we actually have to multiply our 49 million by 47.25. That's because it's not 1 centimeter squared, it's 47.25 centimeters squared on the map. Alright, we're going to get this massive number here. That's in scientific notation. Don't worry about that. It's 2 points. What do we get? 2 point. I'll finish that. Okay, so basically what we're saying there is that a meter cubed. Basically, a meter cubed is the same thing as 10,000 centimeters. Sorry, a meter squared is the same thing as 10,000 centimeters squared. Okay. So basically, what we have to do here is we have to basically say that if 1 centimeter is cubed, 1 centimeter squared in the map equals 49. I think it's billion, or 49 with 8 zeros, centimeters squared in real life. Then we have to find out the area of the map, and we said the area of the map is 46.25, okay? So the area of the map was 47.25 centimeters squared on the map, so we need to multiply 49 and 8 zeros by 47.25. It's done here, and what we get is 2.31525. 2.31525 by 10 to the power of 11. Alright, and this is centimeters squared. Okay, and this is in real life. Now we got to divide by 10,000 to convert it into meters squared. So divide by 10,000 and we get 231,525. So 231,525 and 2 zeros, meters squared. Now the questions asked me to change it into kilometer squared. Okay, so what we need to do there is find out what 1 kilometer is, and 1 kilometer squared is in terms of meters. So if we get a kilometer squared, so you imagine this green box here. Okay, so this is a kilometer squared, which is a kilometer by a kilometer, which equals 1 kilometer squared. And what we know about kilometer is that it's the same thing as 1,000 meters. Okay, so same thing as 1,000 meters by 1,000 meters by 1,000 meters. So there's going to be 1,000 meters by 1,000 meters. Okay, so it's 1,000 by 1,000. Okay, so 1,000 multiplied by 1,000 is going to be 1 million. Okay, so 1 kilometer squared equals 1 million meters squared. So if I divide this number here by, a million, I should be able to find out, what is it in kilometers squared, okay? Just putting in 2 commas here, so I know roughly what I'm talking about. 23 million, okay? So 23, 1, 5, 2, 5, and 2 zeros, divided by a million. 1, 2, 3, 4, 5, 6, and what we get here is going to be 23.15 kilometers squared. So 23.15 kilometers squared, or round it down to 23 kilometers squared in real life. Okay, that's the end of this.